Hi. In this interview with Oliver Pecher, the CEO of eProbe GmbH, we're going to learn about Bruker's collaboration with eProbe and how together they're pushing the boundaries of battery research. I hope you enjoy it. Thank you, Oliver, very much for joining us today. To start with, please can you just give us a quick introduction to yourself, tell us a little bit about your role and the company that you work for?
Yeah, sure. My name is Oliver Pecher. I am the CEO of eProbe, and we provide solutions for battery analysis technologies. So we provide probes, hardware, accessories, as well as all consultancy services that are relevant in the field of researching energy storage materials using magnetic resonance.
So can you tell us a little bit about your background? What's your sort of scientific journey in your career, education and research you've been involved in?
Yeah, I'm a chemist by training, but basically moved very early on into the field of solid state chemistry, and then moved further into solid state nuclear magnetic resonance. And I did my undergrad studies in Germany, and then I did my PhD also in Germany. And then I moved to Cambridge for postdoc with Claire Gray at the University of Cambridge in the Department of Chemistry. And there I sort of specialized in applying the technique of solid state NMR spectroscopy on various type of energy storage materials. So this included batteries, these were supercapacitors, and these were other type of battery materials that you can use. And I was mainly interested in applying the technique of solid state NMR spectroscopy with electrochemistry to study different type of materials. And therefore, sort of, I did also a lot of method development to make this technique more feasible, more useful, more handy, so to say. And I learned a lot here. Then after the postdoc stay, where I was a Marie Curie fellow, I moved back to Germany and joined a company that is called NMR Service at this time. There I was sort of an application scientist and doing also a lot of technical assistance for the customers and services. And then this went on further, and we introduced and we included also the field of NMR spectroscopy applied to battery materials with the company. And this was my major league. And so just recently then, we founded basically a subsidiary of NMR Service, which is the eProbe company. And now we are totally focused on the application of different type of magnetic resonance techniques to research batteries.
So what are the biggest challenges facing us right now when it comes to batteries and energy storage materials?
I think the complexity of a battery is the biggest challenge here. Yeah. So if you look at a battery, you have these different type of materials. You have solid materials in there. You have liquid materials in there, and you have the combination of all these materials functioning together and basically allowing you, to function as a device. Another big challenge is that usually these type of battery materials intrinsically influence the NMR experiment because they are metallic, or they are coming in casings that you cannot penetrate with the technique that you're applying in the NMR experiment. And so you can have a lot of, let's say, interferences between the actual electrochemical experiment, which is the one that is taking place inside the battery, and the NMR experiment that helps you to actually gain insights into the structures and the dynamics of the ions and the other pieces that are moving inside a battery device. Actually, most of these challenges were then already tackled by myself and, of course, the team around Claire Gray and the people I worked with during my postdoc stay, where we did a lot of improvements on the, let's say, feasibility, on the way to assemble the type of materials in different type of cells and containers, and to make these batteries work inside the probe, and then to get the probe into the magnet and actually measure different types of NMR experiments. Yeah. And so from that, some sort of, let's say, prototype developments for various probes and other techniques of automation in NMR spectroscopy originated. This was then sort of, transferred, the knowledge of that, some of that was sort of transferred into the company. And here, of course, in a few iterations, we made it a very, very handy product that is now something that more or less everybody who is just willing to do NMR can actually use.
So those challenges with investigating batteries using NMR, I imagine that gets even harder if you're looking from a more industrial perspective, looking closer to the sort of production state of the battery. If you're doing very blue sky research, you probably have a lot more flexibility in, as you say, changing the setup to look at it. So what are the major differences there in how you have to approach analyzing the battery, looking at the reactions happening when you're looking at essentially developing industrial prototypes?
Yeah, let's say in the prototype development stage of making these probes and the hardware actually more easy to use. Yeah, we were interested in investigating various types of materials, including various type of local sources of information, which in this case is called different type of nuclei, lithium, sodium, potassium, oxygen, and many others. Yeah, and so every measurement was a challenge on its own, although we already had hardware and software in place that we could use to run these experiments. Yeah. For an industrial application, I'm quite sure that you have more like you have the materials that you assemble, you have the materials that you make, then you assemble them in cells. You have these batches of cells that you want to investigate. Maybe 1 out of 100, you want to run sort of a standard experiment, giving you some results, some insights that you can compare with respect to the number of signals, the shifts of the signals, the intensities of the signals, and so on and so forth. Yeah. And therefore, I envision actually a standard operating protocol, including standard hardware and software solutions that we are also working on. And we already have made a lot of progress here so that we can offer the user the complete package, which includes the hardware, which is a very simple to use probe with a simple to assemble and use cell container. Yeah. And then they can just, more or less put everything together, run a standard experiment that we can also help and help them to conduct and do, basically. Yeah. And after that, we also have recently just created some software that we call the ECAT, which is like a software visualization and processing tool that can, with just a few clicks, actually give you a beautiful graphic out of an overnight measurement or over a week measurement of the in-situ NMR data that one can apply. And this will be helpful, at least in my understanding, that users can just run more or less in-situ NMR, which is the combination of the solid-state NMR experiment with the electrochemical experiment on a more or less routine basis.
Yeah. So you mentioned your system is designed to make it easy for anyone that's willing to use NMR to use it for batteries. Why should people do that? Why should people look at NMR? What can it tell you over other techniques that people might feel that they know better?
There is hardly any other technique that is non-invasive, such as NMR itself, and gives you insights into structural information on crystalline as well as amorphous materials. And a lot of materials that are inside batteries, they are actually amorphous, which means if you apply other techniques like X-ray diffraction, you just do not get the information that you are able to sort of source from NMR spectroscopy. And you are sensitive to any type of different chemical species inside the material. And by chemical species, I mean short-living phases. I mean metastable phases even. And this is of course a very powerful technique to learn something about the chemical processes that are happening while you've charged or discharged, for example, your battery material. And from that you can conclude in some sense while a battery, for example, is failing, or while is it working so beautifully. And this then can be translated into further research, into further optimization of existing technologies of your battery, but also to learn something about how to apply new materials in the best and most efficient sense.
Mm-hmm. So are there aspects of the battery chemistry that can be investigated with solution state NMR, with liquid state NMR? And what are the benefits of the solid state NMR? What does that give you in addition to what you could get from the liquid phase?
Yeah, I mean, there is definitely a lot of room where you can apply liquid state NMR when it comes to battery materials. So you can apply liquid state NMR and you can investigate the electrolyte itself. which is done by many people and is a very powerful technique to learn about the quality and the purity of the electrolyte, its performance in simple electrochemical experiments. Yeah, so there you can apply liquid state NMR for sure. However, if you then look into a battery as a device, you always have solid and liquid components, or you have only solid components if we talk about all solid state batteries, for example. Yeah, but let's picture like a liquid and solid state battery. So we have a liquid electrolyte and we have two solid electrode materials. So we have the interfaces between the liquid and the solid, where a lot of things are happening actually that are very crucial for the performance of a battery. And the technique of solid state NMR is then sensitive to all of these processes happening. It can actually sort of help us to visualize what is going on with the interfaces. There are things called the solid electrolyte interface and other things that are happening when the electrolyte is breaking down, or when we have short circuiting of the cell and other things, where solid state NMR can help us to learn something about all the materials and all the processes happening. Because if we do a solid state NMR experiment with a solid state NMR, let's say, equipment, we still measure the liquid components. Yeah, so we see both basically. We get the full package. We get the electrolyte signals, we get the solid material signals, and we get the signals of species that are forming in between. And this is, of course, a very, very powerful technique then by intrinsically. Yeah.
Mm-hmm. And are there any other sort of magnetic resonance spectroscopy techniques that can be applied to battery materials as well? Something like EPR is something that may be complementary to NMR?
Yeah, sure. EPR is one technique, but there are also imaging techniques where you apply also, the basis is always nuclear magnetic resonance, but then you can do some more, let's say, magic. Yeah, you have more hardware that you can apply, gradients and things like that, which just helps us to get actually spatial resolution in 3 dimensions. Yeah, and now just imagine you have like 2 electrodes, and then you have something in between moving, ions moving between these 2 electrodes in one and the other direction. So you get them out of one material and intercalate them in one side, like the anode, and you bring them back. And now you can actually visualize these processes while they are happening. Yeah, and this is doable if we think about in situ pulse field gradient NMR, if we think about in situ magnetic resonance imaging, and so the field is huge where this can be applied. And I think a lot of things have already been shown on a more or less academic scale. Yeah. There is other things where the technique of NMR is really pushed further by, for example, applying DMP NMR and then applying in situ DMP NMR. This is early stage in many ways, but it is happening. People are doing it. And so the products that eProbe in collaboration with Bruker is offering are very good for people to apply basically, one-dimensional or two-dimensional in situ NMR experiments. We also do have a lot of solutions already for imaging techniques and others, but there's plenty of room here where we will surely also provide products in the near future.
Excellent. So talking about where these techniques can be applied, are there particular sectors of the battery markets where either NMR and these other magnetic resonance techniques are more applicable? Thinking about the different segments, you've got electric vehicles and then consumer electronics and like stationary storage for the energy grid. What are the sort of differences between the batteries that are used in these different environments from an analytical perspective, and how does NMR apply differently to these?
I think at some point it's just let's say the scale of the battery. Yeah. So let's consider a battery that we use in a smartphone or in a tablet, and let's assume the battery pack that is actually packed into a vehicle, electric vehicle or other stationary applications. So at the end of the day, if we break down the components that are inside one of these bigger battery packs that are inside one of the electric vehicles, it is still a battery, and we can simplify the scale up of the technique to an analytical level that we can also investigate using an MR. and in-situ NMR. In a sense, we want to learn, and we need to learn about the basics, about the processes, the underlying processes that are happening, to learn how batteries, why batteries function and why not, so why they fail. Yeah, this is surely helpful for all applications, including different types of, let's say, chemistries. Yeah, because for the smaller things like a smartphone or a tablet, we surely want to use most likely like still lithium batteries, lithium technologies, because of the weight. It's very light. Yeah. For stationary applications, sodium batteries are, for example, an up-and-coming technology. Yeah, which can also be investigated by NMR spectroscopy very good, because sodium is a very good NMR candidate to measure. Yeah. But the challenges for a stationary battery that basically, allows you to save all the current that is produced by whatever wind or solar energy is a different one than, applying it to a phone that should last for a week or longer without basically being charged. These are maybe some, ideas about the different technologies and applications here.
Mm-hmm. Does lithium have an NMR active isotope? That's just a side question from me. I'm not sure.
Yeah, it actually has two, which is the good news. Yeah, so there's 7 lithium NMR, which is I would say the most common nucleus to investigate. But there's another nuclei that is called 6 lithium. Yeah, it is many times actually very useful to have one material and then you measure both nuclei in one material. So you use basically a 7 lithium NMR experiment, which gives you certain information. Yeah. And in NMR spectroscopy, we usually measure then sort of, line shapes, peaks, and shifts of these signals. And with the electrochemical experiment going on, these, shifts change and the line shape changes. And if we then want to conclude from whatever happened with this signal, and we can actually measure the same material, the same nuclei, but a different isotope, which would be 6 lithium, we get an independent, intrinsic second source of information, which is many times very helpful for a researcher or for an R&D, scientist in a company to actually, be sure about the conclusions that they draw from whatever from every experiment they actually conduct.
Yes, that's actually a great argument for using NMR to study batteries. If you essentially get 2 experiments in one that are,
you actually not only get 2 in one, it can be more. Yeah, if these materials that actually have lithium or lithium containing, if they also have other NMR active nuclei that we can measure, like oxygen, phosphorus, yeah, we can, without stopping the experiment, without dismantling the battery, so we are still non-invasive, we look into the battery while all of this is happening, yeah, which is an outstanding approach, because other techniques usually stop the device, or they dismantle the device and then they do post-mortem analysis. But here we can look inside, basically, so to say, the battery, with different type of sources of information, like lithium, phosphorus, 6 and 7 lithium, sodium. It depends, of course, what materials and what nuclei are inside the battery, but this is possible. Yeah.
So you were saying before that essentially maybe some of the research that's driven by the larger scale applications will still lead to greater understanding, which will apply to essentially all batteries. What do you think is the most exciting thing about the future of batteries, and how do you think NMR in particular will help get us there?
If we look at, let's say, the past 10 years, 20 years, it is quite clear that we will need more batteries, better batteries with higher efficiency. We are facing already a lot of issues with the materials that actually result from batteries that are already dead, that failed. So we have the waste of batteries, where also we need to come up with some solutions to source something out of the waste that is actually produced. We need to find new technologies for battery materials like lithium, sodium, and then maybe other sources for batteries. And so to cope the demand, or to balance the demand of energy that we need on the world, basically, we need better batteries, because we can produce a lot of energy, but we have hardly the capacities to actually save this energy for the time when we actually need it. And NMR can help us to find and optimize existing technologies and components for batteries, and other energy storage materials, of course, as well. But also NMR will surely be helpful to actually learn something about what about the black mass, what about the waste that comes out of batteries. Yeah. So because if a battery died, it still contains NMR sensitive nuclei that we can use to learn something about what is inside this battery. Yeah. And what is not, and how can we get it out, for example, and how can we, recycle it in some sense. Yeah. So this is why I think the technique is very powerful now and will be and maybe become even more powerful in the future.
Mm-hmm. Yeah, I think you're quite right that there's you have the sort of existing dominant technology of lithium batteries, which, they need to be more efficient, lighter weight, need to recycle them better, all the sort of challenges with that. And then there's also sort of alternative liquid electrolyte technologies that are less established, sodium that we talked about, potassium ion batteries as well. And then there's other sort of maybe even further out sort of technologies, or things that are in being researched in parallel, things like solid state batteries, lithium air batteries, redox flow batteries. So in terms of research priority, like, where do you think those should rank? How much effort should we be putting on optimizing lithium batteries versus helping to mature some of these other technologies that could be more promising eventually?
So my aim is to find hardware solutions to make experiments that researchers need and that R&D in industry and others need work. However, my sense in terms of the battery chemistry is, of course, there. But I think, in terms of improving, or let's phrase it this way. I think there is still plenty of room at the bottom to improve existing lithium technologies. So we should not change the horse that we're on while we're in the river, in some sense. Yeah. Let's keep going steadily. Yeah. However, the demand for, let's say, for example, stationary batteries is also high because of the energies that we need. And so the sodium ion battery technologies will surely also become a more prominent thing to be investigated. And more or less, I think in parallel to that, flow chemistries in terms of lithium air, as well as redox flow batteries, there are huge programs that push these technologies further. And from my perspective, NMR is helpful in all of these things. So that is why I think we should push and move further with all of them. However, it's maybe up to date. It is still more challenging for some of the low gamma nuclei, like potassium batteries and others, to be investigated using NMR. It is more challenging compared to, let's say, lithium and sodium. Yeah. It is also a little bit more challenging maybe to investigate redox flow chemistries, because next to the fact of applying NMR spectroscopy combined with electrochemistry, you also apply sort of another set of experiment, like the flow itself. Yeah. But there are already sort of first solutions for hardware out there. In many of them, we are involved. And so I see this evolving, and I'm pretty sure that also in a few years' time we can come up with some commercial solutions here, and then this will hopefully also help to benefit basically the technologies to improve. Yeah.
Just another question I had about the sodium ion battery technologies. Would that ease some of the pressure on the sort of material supply chains? That's one of the big issues with scaling up lithium batteries is where all the lithium is going to come from. I'm not super familiar with the sodium technologies and the kind of materials that are used, but from what I've seen, it seems like they could be, they could potentially be a bit less problematic in terms of sourcing the actual electrode and electrolyte materials that are needed compared to the lithium and cobalt and everything else that's needed in current technologies. Do you think that's a factor as well?
It is a factor, sure. I mean, sourcing the raw materials that you need to produce sodium ion batteries is, compared to some of the lithium technologies, easier. However, the challenge here is still that although on a first glance, some of the chemistries that underlie lithium ion technology and sodium ion technology look very similar because of lithium and ion, they are very like sort of similar isotopes or similar elements. Yeah, they are not, and this basically results in different sort of performance, or in maybe even in some issues of these sodium-ion batteries compared to a lithium-ion technology with the same or very similar structural feature, structure of the material that we use. Nevertheless, it is worth going both directions, basically, because at some point we will drain out our lithium resources. And if we don't have enough capacity already in the recycling and in the reusing of lithium ion, we will run into a problem. Yeah? People are working on that. NMR can help on all these ends, as I outlined earlier, in my opinion. And sure, I mean, even if it's not the same using sodium-ion technology, yeah, we will find other ways, maybe even better ways. We don't know yet. Yeah, but it is surely a challenging task, which is why people need the best hardware they can get. To not, have to play with actually, getting the experiment to run. They can ask us for doing that for them. We help them. We consult them on what is possible. And then this will hopefully, benefit their research or their R&D or their quality controlling of manufacturing and other things.
Yeah, excellent. So you talked earlier about the sort of different ways that you've been trying to make NMR more accessible for this industry. What do you think is the most important thing that can be worked on to make NMR as accessible as possible to a wider user group, particularly in industry where there's often some resistance to adopting the more complicated technology?
Yeah, I mean, the creator of saying simple things work and complicated things don't is, I think, quite true here as well. Of course, if we start, or when we started to improve the method, improve the method of in-situ NMR being applied to various type of energy storage materials, we thought about this one probe that can solve a lot of questions, right? That can help us to gain insights into various type of materials using all the nuclei that are out there in various magnetic fields. Yeah. When it comes to applications in the industrial sector, I think that the question they have there is much simpler. They want to know, is my material fine or is it not? And we are focusing on this type of material with this type of nuclei. How can NMR help us here? And for exactly these questions, we are more or less already capable of providing equipment, namely an NMR probe combined with a certain set of cells where people can put in their materials. Yeah, a standard that people use actually to test their battery materials or their batteries is a so-called coin cell. Yeah, so that's a little stainless steel thing that you put more or less anywhere, and this is also done in the lab scale, just to assemble everything, and then you put it in a cycler, and then you see the electrochemical performance of your material. And we already do have a probe actually that can hold and handle one of these stainless steel cells that you just insert to the probe. Then you insert this probe to your magnet and you press basically go for the experiment. And then you run your in-situ NMR experiment while you also run you run the electrochemical and the NMR experiment at the same time, which is in-situ NMR. And so this probe combined with the coin cell is surely something that simplifies the work people have to do a lot, because they can actually use the device that they already took out of their production line to test into their probe. Yeah, it's the same with pouches, for example. A lot of applications in the sector are used as pouches, like aluminum covered pouch cells or something like that are then rolled up or put together into bigger battery packs. Yeah, and with the challenge that we did overcome to measure through actually these stainless steel coin cells also helps us to measure directly into these pouches made out of aluminum foil or something like that. It's not only aluminum foil, it's more elaborated, but in a simplified way. And so this is surely one way to improve that. And if we then combine this with software tools that allow the user afterwards to use the raw data from the electrochemistry experiment as well as from the NMR experiment, and just basically load these two data sets and get very quickly a graphical, analysis and which shows you the electrochemistry data as well as the in-situ data with all the signals that are out there. This is something we already have, and we can tweak that for a particular user if they want to do some, line analysis, peak fitting, or something like that. Yeah. So I'm pretty sure that we can, or we are working on that actively, actually. But we will. I'm sure that we can also provide that in the near future, so that people have this more or less plug and play technology when it comes to the in situ part for a particular research question. And I think this is really what people will consider to be more, useful maybe for their, R&D facilities or whatever.
So finally, then, in a similar line, but from Bruker's perspective, what do you think will be the most important thing for them to develop?
I think the best way to move further here, and there has already been a lot of progress here, is to offer complete systems. Yeah, and Bruker can provide, and they now can, and our two companies together can. They provide the a reasonably high magnetic field strength, like 400, 300 megahertz, combined with one of the beautiful Neo consoles, combined with an ex situ probe like the magic angle spinning MAS probe 4 millimeter, because you usually combine some of the ex situ work with one of the eProbe Bruker in situ probes. Yeah, for example, then with a bunch of different types of in situ cells that we call the plastic cell capsules, which are very modular and versatile to use. But also maybe combine it with some of the coin cells, with some of the software packages that I outlined earlier. So they are able and should be able to provide this complete package, including the training, the consultancy on, how to make the battery work inside this sort of in situ cell, how to set up the experiment, and then the user can basically do all of that on their own. Yeah, and as I said earlier, this is already now happening. So this is what we can provide. So you can run these experiments 24/7 if you want. You can run them in overnight and out of hours in the lab, which is also a crucial factor here, because you usually don't have your technicians around the lab 24/7. But the hardware that we provide can be monitored remotely. It can give you sort of signals if something fails, and so on and so forth. So this is surely the route we should go, and as far as I can tell, we are going it. But of course, we're always open-minded and open for the needs of the actual of the users.